Okay, let me try to show you the nuts and guts of how this electric field mapping lab works. This is the main piece of equipment. And let's say, for example, I wanted to convince myself what the electric field lines look like for an electric dipole. So there's something called 2 points within a field. That's the same thing as electric dipole. All of the dark gray is semiconducting, and then the silver is conducting. So I can use a battery as a source of electric potential difference. So I know we're getting a little bit ahead of ourselves talking about electric potential in this unit of study, but it's not difficult to understand that the positive terminal of a battery is a source of high electric potential, and the negative terminal of the battery is a source of low electric potential. And I can use that potential difference to oppositely charge conducting materials. So right now there's a potential difference of 1.5 volts because I'm just using one battery. I could connect to the negative of the other battery. Now there's no connection between these two. So if I use this wire to connect the negative terminal, so let's think of it like this. We can define electric potential to be 0 anywhere we want. It's kind of like creating a reference system for potential energy in your study of mechanics. The value of potential energy is irrelevant. All that matters are changes in potential energy. So I'm going to define the negative terminal of this battery to be 0 electric potential. Then this point is 1.5 volts higher than that. This is still at the same value because it's just tied together by a wire. And this is another 1.5 volts higher of electric potential. So from here to here, the total potential difference is 3 volts. That might be an over-explanation, but I want to be clear about that. So if I want the electric potential at this conductor to be 3 volts, I can touch this here, and I can make the electric potential on the other one 0, and that way I'll say this is the negative and this is the positive, and the potential difference between them should be 3 volts. But I don't want to have to hold these on here. So instead, I flip this panel over and I can attach this to the bottom. So there's a couple of screws that go in to hold it in place. And here's what's happening. This piece of metal just is held at the same electric potential as whatever I plug in here. So from the battery, I connect the black wire and I set this whole piece of metal at 0 electric potential. I plug in the red wire to the other input here, and then this whole piece of metal is at the 3 volt high electric potential. And then this is tricky. This bolt is made obviously of metal, and so when I put it on here, the contact between this metal and this bolt and where it screws into just maintains the electrical connection, right? Okay. So yeah, now indeed this silvery circle is at 0 volts, and once I put this in, this one will be at 3 volts. And effectively, what the battery's doing is pulling electrons off of this piece of metal, conducting them through this metal rod, through this wire. There's some ions that interact in the chemicals of these batteries, and essentially then excess electrons now end up on here. Electrons have been conducted off of this metal and onto this metal. So this is negatively charged, this is positively charged, this is the low potential, this is the high potential, and the potential difference is 3 volts. So leave it like this. Now I have a device that measures differences in electric potential. We call it a voltmeter. This is actually a multimeter. When I turn it on, there's several settings. When I click it here, it can measure electrical resistance. If I click it here, I can put it in line with the circuit and measure how much current is flowing. But when I set it, where do I want to be here? To the V, I'm telling it I want it to be a voltmeter. And since voltage means difference in electric potential, you always need to connect this to one point and this to another point, and you're comparing the difference in electric potential. So hopefully I've got this set up. You can read the numbers on here. Right now, if I connect these two together, it should for sure read 0, right? If I touch this one here and then touch this one here, I hope it reads 3. And sure enough, yeah, 3.043 volts. If I touch both of them to the same point, this is the 3-volt potential. But there's no, the difference between +3 and +3 is 0. Okay? Now, if I put the black one here and the red one here, it's going to read -3. Sure enough, -3.04. Okay, so I want to put the black one at the lower potential, the red one at the higher potential, and I can read the potential difference. So make a prediction. I'm going to hold the black wire on the voltmeter at the low potential, and instead of touching this at the high potential, I'm going to put it halfway there in this semiconducting material. What do you think we're going to get? Any surprise here? It reads about 1.5 volts. As I slide higher toward the positively charged, the potential difference goes up. As I slide it closer to the negative charge, the potential difference goes down. It's a little inconvenient to do it this way, so what we do is we flip it over, and now I can't see what that pattern of charges are on the top surface. There are a bunch of different templates on here. Okay, this might be the one I'm looking for. Nope, that doesn't match up. This has several templates in one. Here we go, different envelope full of templates. This should be the one. There's a lot going on this one, but if I flip this over, hopefully I can find, there it is. Okay, so with this one, this hole and this hole match the pattern of electrodes that are on here. I know there's other holes on here, but that's fine. I don't need them. So there's actually tiny little posts and tiny little holes here that'll hold that. So I just make sure that it aligns, and it does. So when I flip this over, if I set it like this, let me just double check. Yeah, this hole and this hole match up. So I can take a piece of paper, set it on here, and this is kind of neat. There's a little spring activated feet on here, little rubber tips. So if I just take and push down, then when I pull back up, these rubber grips will grab that piece of paper and it's not going to slip, so I don't have to tape it down. So now if I take this pattern, set it on here, again, I always want to double check. I'm not going to be tracing everything. I'm just going to trace the parts that happen to match up. Yeah, this hole and this hole will do the trick. So I circle this, and I circle this one. High potential, low potential. So I make a reminder. That's the positive. That's the negative. I can ditch the template. And then I always want to have my low potential reference of the voltmeter to be here. I want to hold this here and effectively slide this one all over the place and see what the difference is in potential compared to my 0 reference point here. But I don't want to have to hold this under here. So I could connect it here. I think you understand the electrical connection carries along this metal bar, and it's basically the same thing as holding it there. Okay, but still I don't want to have to reach under here with my hand and move all around. So I'll connect it to this device, plug in, and then there's a wire that runs all the way down here and touches a little piece of metal. So when I put this below and move around, you can see on my voltmeter, if I go all the way over here, it's going to be very close to 0. As I slide this way, I get closer and closer to 3. If I'm somewhere right in the middle, I should find 1.5. In fact, if I can find the point that says 1.5, there's a little hole here that I can use to make markings. So hopefully you can read my screen okay on the voltmeter. It dances around a little bit, it's hard to fine tune. So to the best of my ability, I'll make a dot where it's 1.5. And then I'm going to find another one that's 1.5 across the width of the paper. So where's another place that's about 1.5 volts? Right about there. Let me find another one. Maybe right about there. Let me find another one. A little tedious, I know. Maybe about here, okay? And I'll go across the full width of the paper. Yeah, maybe about here. Here. About there. Okay. So now I have several dots that all represent the same amount of electric potential. I'll write next to one of those 1.5 V as a reminder to myself. Let me see if I can find the place where the electric potential is all 1 volt instead of 1.5 volt. Okay, right about there. Where else? Right about there. Can I find another one here? Yeah, right there. So you get the drill. I'm searching for lines of equal electric potential, which we say lines of equipotential, right? If I could connect every set of dots that represents the same electric potential, I find a line of equipotential. Well, you should know that electric field lines intersect lines of equipotential at an angle of 90 degrees. So if I can create a good pattern of equipotential lines, I can reverse engineer, so to speak, the electric field lines. And we have a sense of what the electric field line should look like for a dipole. So this becomes a lab that we use to confirm what we suspect about the electric field lines. So notice we cannot directly measure the electric field. For one thing, even if we did, our measurement would be just a numerical value if there was something that sensed electric field, right? I doubt there'd be something that could give us the magnitude and the direction. So electric field is a vector quantity, but electric potential is a scalar quantity. So this is great. I'm measuring magnitude of electric potential because that's all that it is. And so you can see this other set of dots, and I'll label next to that 1.00 volts. Well, I'm going to find different values using this exact same process. Maybe the 2 volt will be a set of dots that form a curved line here. Kind of interesting that the 1.5 volt, it appears that it's almost going to just be a straight line down the middle that connects those, whereas the 1 volt clearly has some curvature to it. So you can probably make a prediction of what the lines of equipotential are going to look like. I'll save you the time of watching me do it. In the end, you'll see what I produce for this pattern, and then the point of the lab is to carry on and do a different pattern. You might be interested in what do the field lines look like for oppositely charged parallel plates. So I can disconnect, flip this over, unscrew the bolts, and replace it with the parallel plate arrangement. But now I'm probably going to need a different template and a new piece of paper to create my equipotential lines in this case. So I flip it back over, I reconnect from the battery, low potential from the battery here, high potential here. I want my reference point of low potential of 0 volts on the voltmeter to be consistent with the negative terminal, and I want the high potential reference of the voltmeter to be something I can probe all around on the bottom surface, so I plug into here. So everything's reconnected. I can remove this paper now, grab a new one, and first make sure I'm working with the correct template. So this template, it doesn't look like it matches up. Find the other template. And again, it's got a lot going on. I think this template serves more than one pattern of conductors, so I only have to trace the parts that match. Let's flip it over and see. Yeah, sure enough, I see it. So when I flip this over, I can insert a new piece of paper, use the spring-activated rubber nubs, set this on here in the manner that I think aligns, but always double check it. Yeah, when I flip it over, I can see this is going to match up, so I'm safe to trace out this pattern. Again, I'm not tracing every single cutout on the template, only the parts that match up with my actual electrodes. So a little bit of thoughtfulness has to go into this, right? So I can remove the template, I think. Easier said than done. My goodness, there we go. This is the positive, this is the negative. Don't forget to do that. And no surprise, if I put it about in the middle, I'm going to get something close to 1.5. Closer I get to the positive, the closer this goes to 3. Closer I go to the negative, 0. And I'm going to look for points that are all at the same electric potential that I can connect to form lines of equipotential. And again, I'll fast forward and give you the results for that. Another interesting arrangement might be, what if I have a conducting sphere and an insulating sphere that sit in the middle of a dipole? So I'm going to charge this pole, and then sitting in the electric field created by this dipole is a conductor and an insulator. So the same process, I'd flip this, remove the other one, find the correct template. So that would be a good one to work with. And the last one to work with, we call it the Faraday ice pail. And what it's meant to convince you is it approaches a Faraday cage. This isn't a completely enclosed conductor, but it's a very hollowed out conductor. And a Faraday cage is a completely enclosed conductor in which there's no electric field on the inside. And I'm sure you've caught my lecture that explains how any enclosed conductor acts as a Faraday cage. Your car in a lightning storm is a Faraday cage. You don't want to get out of your vehicle. It's the safest place to be. There, no electric fields can get inside because your vehicle's made out of metal and it's completely enclosed. So in any case, we can charge this pole to negative. Actually, how about we make this one the positive, okay? And then we make the Faraday's ice pail or Faraday's ice bucket the negative. And so electric field lines are going to emerge from here. They've got to terminate somewhere on here, but the question, where do they terminate? Did the electric field lines make it into the interior? Well, we'll go through the same process again, plotting the lines of equipotential, and knowing that electric field lines have to cross the equipotentials at 90 degrees, you can see what pattern emerges for the electric field. So for at least two of them, I would expect for the dipole and the parallel plates, you have a good idea going into it of what the field lines ultimately are going to look like. And then it's probably a bit of discovery to figure out what the electric field lines are going to look like for the conductor insulator and for the Faraday's ice pail. Okay, there you have it. This is how the equipment works. Next step is to share the data.